Swayam Prabha. Digital India. Educated India.
The first is something called a depth-first spanning tree, right? So what is a depth-first spanning tree? So anybody tell me what is a spanning tree of a graph?
The minimum possible path which covers the breadth of the graph. Basically, it's used in these networks, right, where you want
Yes.
to span the entire network.
Exactly. So a depth-first spanning tree is that, so you can construct a spanning tree by just doing a graph traversal. So you just do a graph traversal and you do not traverse any edges that form loops, that rather not should not suggest loops, but even acyclic tags. So you should not cover any edges that leads you to a node that you've already visited, right? So you just use any graph traversal that traverse the nodes but does not visit any already visited node again, right? Because you're not visiting any unvisited node, you will always fall into a tree. It will always give you a tree to look at the nodes that you have covered. Look at the edges that you have covered. That will always fall into a tree. And if you use a depth-first traversal to get this tree, then it is called a depth-first traversal. As simple as that. Right? So you do a DFS on a control flow graph. I'm sure all of you know how to do a DFS search. So you do a DFS search on a control flow graph. The spanning tree that falls out of that DFS search is referred to as the depth-first spanning tree. So how do I do this? If I really want to look at the algorithm, you start with the entry node, you mark it visited. Whatever you hit upon, you mark it as visited. Then you look at only the unvisited successors of n. So let's say S is an unvisited successor of n. You go through only those successors of n which are unvisited. So you start from a node and you look at all the successors that are not visited yet. Like if this is visited, you don't even go there. You only look at the ones which are not visited. Then you, whenever visit any such successor, add that successor to the edge, to the tree, and then recurse on this edge. Again, you look at this, again you find out its successors, find out which are visited, which are not visited. Whatever are not visited, you add those edges you add to the tree. Whatever is visited, you leave it out. Again, you recurse on this. Again, you recurse on this. Again, you just find out what are the different nodes, different successors, what are visited, what are not visited. Again, whatever are not visited, you mark them into that, and you do in a depth-first manner, right? So you will first traverse this, then you backtrack and do this, then you backtrack and do this, then you backtrack. So you make one DFS traversal, and the tree that falls out of that is referred to as the depth-first manner. It's a very simple algorithm, and I'll not spend much time because I'm sure you have seen such algorithms before. At least you have seen a spanning tree algorithm before, so this is just that. Now, once you do a depth-first traversal and construct this depth-first spanning tree, once you have the depth-first spanning tree, now you can reclassify. You can rather there's only classify. So you can now classify the edges in your current control flow graph into 4 categories, right? Depending on the depth-first spanning tree that you have got. The first category is what are called tree edges. So these are all edges which are also present in the depth-first spanning tree. So if there is an edge which is present in the depth-first spanning tree, then you mark that edge in the control flow graph as a tree edge. Then the next type of edges are called forward edges. So forward edges are all edges that go from an ancestor of a node to a descendant of the node in the depth-first spanning tree. Right? So I will give you an example. Then you have retreating edges. So for these two, you will look at your depth-first spanning tree. These are edges which are directly present in your depth-first spanning tree. These are paths present in your depth-first spanning tree. So if there is a path from A to D in your depth-first spanning tree, then an edge A to D is referred in the control flow graph is referred to as a forward edge. Then you have something called retreating edges. Retreating edges go from So, okay, so let me just draw a tree and say, let us say this is the depth first spanning tree. Let's say this comes out to be the depth first spanning tree. And okay, so now, and I'm saying the direction goes like this. Doesn't really matter. So now, let's say I have a control flow graph which goes from. So this particular edge in the control flow graph, because it is also present in the depth first spanning tree, is basically this edges in the so this is the control flow graph. So this is referred to as a tree edge. What is a forward edge? So let us say I have a edge A to F. Right? Now there is no edge A to F in this tree, but there is a path from A to F in this tree. So A is the ancestor in that, and F is a descendant, right? So this particular edge becomes a forward edge. Then I have retreating edges. So if I have an edge that goes from F to B, right? So if I look at my graph, so this is an edge that goes from F to B, but there is an edge from B to F in the spanning tree, right? But I am going in the other direction. These edges are referred to as a back edge. In fact, it does not even have to go to the immediate successor. It could have gone to the either A, right? So when F to A would have been a back edge. Sorry, it retreating edge. And then there are cross edges. Cross edges are edges that cut through the control flow graph, the subtrees in the control flow graph. So for example, if there is an edge from B to G, for example, right? If there is an edge from B to G in the control flow, so it goes from one subtree in the spanning tree to another subtree. So there is no ancestor-descendant relation between these two edges. So then this B to G will be a cross edge. Now, the set of tree edges, forward edges, and cross edges together are referred to as the DFS DAG. So they surely form an acyclic path because the retreating edges are sort of creating an edge in the opposite direction. So if I remove the retreating edges, the remaining edges together would form a DAG. And that is called a depth first DAG. Okay, I've said a lot of things. So let us try to understand them from the example. So now we have some control flow graph. And let us say I do some DFS traversal on this. And then I get this particular graph where the solid edges are the solid and the dotted edges together are all the edges in my control flow graph. And the solid edges are my tree traversal. So they are the edges that are there in my depth first spanning tree, right? So now can you give me one edge which is a tree edge? Can somebody suggest an edge which is a tree edge?
The edge from 1 to 2 or node 1 to 3.
Very good, very good. So these are all tree edges. So this is a tree edge, this is a tree edge. Can somebody tell me a forward edge?
From 7 to 4.
7 to 4. But 70. So what is a forward edge? A forward edge is when there must be a path from. So, okay. So let me open it for the class. Can somebody tell me? So 7 to 4 is not a forward edge. Can somebody tell me what is the type of edge that is?
Retreating.
That's a back edge.
Yeah, no, it's not a back edge. It's a retreating edge. There's a difference between a retreating edge and a back edge. A back edge is where the dominance relation holds. Retreating
yeah.
edge is when. So yeah, so there is a retreating edge because this is an ancestor in the tree, and this is a descendant in the tree, and you are going from a descendant to the ancestor. So that is why it is a retreating edge, right? So this particular edge is a retreating edge. Can somebody tell me a forward edge now? Now it is easy.
4 to 7. 4 to 7.
Exactly. So 4 to 7 goes from a ancestor to a descendant. So this is a forward edge. And can somebody locate a cross edge?
So 5 to 7.
Very good. There is 5 to 7. This is a cross edge. 2 to 3 is a cross edge. Right? Excellent. I think we have understood it. Right. So now you can classify your edges into these 4 categories.
Wait, isn't 4 a dominator of 7?
Yeah. So
in that case, 7 to 4 would be a back edge.
I did not say it's a back edge. I said it's a retreating edge.
Okay.
So back edge and retreating edges are different.
Yeah. Can you go to the previous slide again? I'm a bit confused between these. No, the previous one. Yeah.
So this is the definition of a retreating edge. You create your depth first spanning tree, and the node from the descendant to an ancestor is a retreating edge. What is a back edge? You use a dominance information to construct an edge. So a back edge is a node edge from source to target, such that the target dominates the source. These two are coming from a very, very different family of things.
Sure.
Right?
Thank you.
So this is only using the dominance information, and this is using the depth first spanning tree information.
Yeah.
This is a very good question. Thank you for this question. Really, thank you for this question, because this is a doubt that many people have. Interestingly, right now it seems that there is no relation, right? Because one of them is depending on the dominance information, the other one is from the spanning tree. But we will show that there is a very interesting connection between these two edges, and we will talk about it. But for now, you understand that they are different, right? Are you clear with that, right? Like whoever had the confusion?
Yeah.
Okay. Very good.
Can you show these definitions once again? Yeah, sure. Just 1 second.
Also, these retreating and cross edges would be there in the DFS presentation, not in the spanning tree, right? Because in the spanning tree, we would never revisit a node, so there won't be a retreating edge in there.
They are not in the spanning tree. They are part of the DFS DAG, right? So that's what I said.
Okay.
So the tree edges, the forward edges, and the cross edges, they together form the DFS DAG. Again, remember this term. So this is an acyclic graph, right? So this will always form a acyclic graph because you have removed all the retreating edges. So this is surely going to be the acyclic. Okay. So now the next thing is that we define what is called a depth first number. So a depth first number is basically it's a number which is the reverse order in which we last visit a node in its depth first traversal. So if you do a depth first traversal and a node might be hit multiple times and exit multiple times, the last time it comes out of that, it is not even hit anymore. That is referred to as, and then if you reverse it, that becomes the depth first number. I'll explain it. In some sense, it is the reverse of the post order traversal. You know what is a post order, so you construct the post order of your graph, of your nodes, and just reverse it. That gives you a number for every node in the graph. And that is what is referred to as a depth first number. Right? So let me just go back to this and try to explain what is this depth first numbering. So now let us say I show you the depth first traversal by this depth first DAG, depth first presentation. Now, now I want to give you her. So now what you can do is, now let us try to do a depth. Let's see what this depth first traversal might have looked like, right? So it must have been, first you would have visited 1, then you would have visited 3, then you would have visited 4, then you would have visited 6, because 6 is goes deeper. Then you would have visited 7, then you would have visited 8, then you would have visited, say, 9, and then you would have visited 10, right? So after visiting 10, you would have backtracked into 8, then you would have backtracked into 7, then you would have, in fact, there is a backtracking in between also, so I missed that. Between 10 and 9, there would have been a backtrack of 8. Then you would have visited into 7, then from 7 you would have backtracked into 6, then you would have backtracked into 4, from 4 you would now visit 5, then again you backtrack into 4, then you visit 3, then you visit 1, then you visit 2, and then again you backtrack into 1. Now you just look at the last time a node is visited. So this is the last time 1 is visited is this. The last time 2 is visited is this. 1 has already been taken. Last time 3 is visited is this. Last time 4 is visited is this. Last time 5 is visited is this. 4 is already been visited, so let's not worry about it. 6, last time 6 is visited is this. Last time 7 is visited is this. Last time 8 is visited is this. Last time 10 is visited is this. 8 has already been visited, let's not worry. 9 has not been visited, so last time I visit 9 is this. 8 has been visited, 7 has been visited, 6 has been visited, 4 has been visited, 3 has been visited, 1 has been visited. So I don't care. Now I take this circle, guys, and then turn them over. I write them in the other direction, in the reverse direction. So if I write them in the reverse direction, then it is 1, 2, 3, 4, 5, 6, 7, 8, 10, 9. So this is their depth first numbers, right? So if I write the depth first numbers of these nodes, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, and this is 10. Got it? Any questions?
Wait, what did you call this ordering? What's the name of this?
Depth first number, DFN.
Okay. Okay, yeah, I was thinking on the lines of topological sort, but yeah, this is different.
This is a numbering. This is not a sorting.
This is not topological sort.
This is okay. Sorting and numbering are different operations.
Yeah. Okay, sure.
Numbering is basically constructing a map from a node to a number. Sorting is basically putting the nodes in a certain order. Right? So they are different operations. Like searching and sorting are different operations, right? So these are different operations. So the first numbering is giving you a number to every node in the graph. It is saying that if I ask you the DFN of 1, it will return me 1. So if I ask you the DFN of 9, it will, the DFN of 9, it will return me 10, right? So it gives you a number. So I'm just trying to assign a number to each node in the graph. But this, if you look at this, if you sort the nodes in the DFN order by their DFN numbers, it is a topological sort, or it is a topological sort, right? Did I sort of point out the difference well?
Yeah.
Okay.
No, but don't we mark each node when we first hit it rather than when we exit it? In topological sort, if I remember correctly, we mark each node when we hit it.
I am not talking about a topological sorting algorithm. I'm just saying that this gives you a topology. So this sorted order is a topological sort.
Okay. No, but then how come?
Okay,
2,
let me put it in a.
Let me put it at the end.
Okay,
because 2 is independent.
Let me put it in a different way. So I am giving you another algorithm for topological sorting. Right, so I'm saying that you first assign the DFN numbers and then sort them by the DFN numbers. That will be a topological sort. That is all I'm saying. Okay. So now, what is your objection?
No. Yeah, let's finish this, then we'll discuss.
Okay. So understand one more thing, that a topological sort is not unique. There can be multiple topological sorts.
That's true. Yeah, definitely.
Like in this, for example, for even this very case, I could have very easily rearranged 10 and 9, right? It would not have changed. Both of them are right topological. Great, awesome. So I'll not. This is it's a simple algorithm. Now the question is, how do you put your how to write this DFN numbering algorithm. I mean, it's there on the slides, but you should go back and try to think about this. Now, let me ask you some questions. Can you find some property over depth first numbers and the type of their nodes, right? So if I give you the DFN numbers of the participating edges, so let's say I have an edge A and I have an edge B, and I say the DFN number of this is N1 and the DFN number is N2. If I give you the DFN numbers, by these DFN numbers, can you tell me something about what type of edge this is? So interestingly, as it turns out, that for tree edges, forward edges, and cross edges, if you have an edge going from A to B, then the depth first number of A is always going to be less than the depth first number of B. Again, you guys should go back and try to prove this. This is a very simple proof. Again, a very simple proof. But it will actually clarify things a lot more. You will understand exactly what's going on. Right? And if you have retreating edges, where you have an edge going from A to B, or A, I forgot. So this is the other direction. So if you have a retreating edge, then the depth first number of A is going to be bigger than the depth first number of right? So one interesting thing that falls out of this is that it actually gives you a way of classifying. It gives you a classification algorithm. It allows you to classify nodes which are retreating nodes, retreating edges, and all other edges which are forward, cross, or which are parts of the DFS stack. So this is a very simple classification algorithm. You just number all the nodes, give them some DFS numbers, and then just for every edge you just try to find out like what is the order of these numbers of these nodes, and that tells you whether it is a tree edge, it's a forward edge, cross edge, or a well, I mean, you'll not know among these guys that what type of edge this is, but you will be able to classify it to a retreating edge or not a retreating edge. Okay. The next is the DFS picks up the, so let us say the way you are doing this DFS traversal. So I have whenever I'm doing DFS, I can choose one successor. So let us say I always choose the leftmost successor, right? So if I do that and I create that DFS tree, right, and mark the DFS nodes, can you tell me what is the direction of the cross edges? Which direction will the cross edges go? Will they go right to left or left to right?
Left to right.
And no, they will actually go right to left, because the DFS will go from right to left. So whatever is not in the DFS will be a cross edge. So as it will turn out, they will. So if the DFS, if the DFS always picks the leftmost thing, then the cross edge will always go in the other direction. It will always go from right to left. One moment, just keep me on that. Okay, good. So the next thing is that, so this I've already said that this gives you a way of identifying retreating edges, because I can just look at their numbers, the order of their numbers, and see that. Please remember. Okay, so this is we are clear with. So this depth first numbering is very useful, very, very useful. You can understand that. Now let me have a quiz, and as if I've not been having a quiz, but anyway. So the first question is the depth first spanning tree unique? If I run my DFS spanning tree, so there is no choice of successes, but if I just run multiple DFSs, so first of all, is my DFS traversal unique? That is what is somewhat asking, because whatever comes in the DFS traversal becomes a DFS tree.
No.
No.
As we can visit the leftmost child or rightmost child first.
Exactly. I can decide to pick any of the childs, and depending on which child I pick, I may or may not. But doesn't, so this particular, for example, you take this particular graph, right? So no matter if I pick A first or B first, my depth first tree is still the same. So can you give me a case where it will not be the same?
So in our previous example only, I think that would change.
Okay. So can you create one example quickly?
Yeah.
Like for example, if I do this, if I add them into a D, then it will have different depth first traverses, right? So one possibility is that this could be a depth first tree, right? And then this becomes a cross edge. Or the other option
Yes.
could have been that this is my depth first tree, and this becomes a cross edge, right? So there can be multiple. The DFSTs are not unique. Depends on the traversal. So is the classification of nodes into tree, forward, and retreating and cross edges unique? Again, it is not unique. If the DFS tree is not unique, then how can they be unique? That we again saw in the previous example. Right. Now the question is, are back edges uniquely determined?
Yes.
Excellent.
Yes, because dominator relation is always unique.
Absolutely. Very good. Very good.
Yeah.
So it has nothing to do with the traversal, right? It has domination relation. So so back edge is only defined by domination relation. So it is surely unique. So are all back edges always retreating edges? And that is where we are coming to the very interesting part of it.
No, as
No, because
retreating
it's
edges
not.
can vary.
What can vary?
It's not necessary.
The retreating edges, but back edges are uniquely determined.
Yeah, they're uniquely determined. That is fine. So what?
And retreating edges can vary. I mean, they can change depending on the traversal.
The retreating edges can change depending on the traversal. Can you show me a graph where it will change depending on the traversal? The retreating edges will change. So what we have seen so far was there was a change between something becoming a tree edge and a cross edge. That is what we had seen. But can you create a case where back edges and retreating edges will exchange with any of these other edges? The forward direction edges? The dag edges?
I think it's because retreating edges can be to node which is not a dominator, whereas back edge will always be to a dominator. So this is false.
No, so but you have to give me a counter example. You have to say that why it is false. No, I did not get that argument. What is the argument?
The argument is that retreating edges can be between arbitrary nodes. Retreating
But
edge.
how can it be? No, there is still a structure, right? So there is a nice property. I mean, you cannot just call anything a retreating edge. There is a nice property, right? I mean, even if you do by this, it is always the case that retreating edges, the DFS numbers are going to be in the other direction. What if there is a relation between DFS numbers and dominators? I mean, there can be a relation, right? I never said that there is no relation. I mean, you are doing DFS in some order, right? I mean, DFS is not an arbitrary algorithm. You are going things methodically. You are going through them in some order.
So we can, I think, we can create one graph if you can.
Okay, sir, can you tell me what is the graph?
So first make a node and two child nodes.
That's a node A. It has two children,
Yeah.
B and C.
B and C.
Okay.
And connect the C to B and B to C. I mean, there is one edge from B to C and
Very good. Very good. So now what happened here?
So if you like pick the leftmost traversal, then the retreating edge would be B to C, and the other way around it would be C to B.
Okay, so which one is so now your tree edges are, this is a tree
Yeah.
edge, this is a tree edge, and this becomes a forward edge.
Forward edge, and the retreating edge would be like C to B.
This is a back, this is a retreating edge.
Yeah.
Acha. And which is a back edge here?
I mean, I just wanted to show that retreating edges can change. I didn't. Okay, let's think about the back edge here.
Okay, we'll come to that. So then you are saying this is one case, and the other case is that if your edges are in the other direction. So this could be a forward edge, this could be a forward, the next edge, and then this can become a forward edge, and then this can become a retreating edge. Okay, good. So you showed at least it is the case that retreating edges and other edges can interchange. It is not that it is only between the edges. Good. That's very good, very good. So are all edges? So, but we have not answered this question yet.
But won't all back edges be retreating edges, since in a domination relation we go forward and in a back edge we go backward to that node? So they would be retreating, but all retreating won't be back edges, but all back edges would be retreating edges.
Okay, let us come to that question. So are all back edges always retreating? Let's answer this question first. So that is true. That is what you were saying, right?
Yes.
Okay, so yeah. So okay, so you have already argued that all back edges are going to be retreating edges. So the question is the other direction now. Are all retreating edges back edges?
Yeah. No.
Can you give me an example? Okay, we'll see. The next question is that, is the DFS DAG unique? And it is not unique. You already showed that, right? Because there was an interchange between so you remove the retreating edges to create a DAG, and you already showed that the retreating edges can change. So the DAG has to change. Like you guys already gave me an example where there was so what is a DAG? The DAG is we remove the retreating edges and we get a DAG. That's the DAG. So you already showed that the retreating edges can change, can exchange between, there can be a swap between the retreating edges and the other type of edges. So if that is the case, then the DAG can change. And the example that we have is exactly the same example that you gave me. This is exactly the same example. So if you have this sort of a graph, now can you identify, just to get deeper and try to understand everything, can you identify the back edges in this?
There is no back edge.
Excellent. There is no back edge. Absolutely, there is no back edge. Because what is the dominance tree? The dominance tree is 1, 2, 2, 2, 3, 2, 4. That's your dominator tree. And you can see that, like, of course, the others, none of them flow the other direction in the dominator tree. And it is only possible for 3 to 4 or 4 to 3 to have been something, but none of them is a dominator of the other. So they cannot be back edges, right? So there are no back edges in this book. But we already saw when we were analyzing it, that any of these two edges can become a retreating edge, depending on which DFS traverse you take. Right? So this is a case where there is a retreating edge, but there is no back edge. And the retreating edge can swap between a different type of edge, depending on the DAG that you get, the DFS tree that you get. Right? So there is no back edge in the graph. Either of 3, 4 or 4, 3 can become a retreating edge. The other edge will become a tree edge, right? And as the retreating edge changes, the DFS DAG also changes, depending on the DFS. So the DFS DAG is also not unique. Right? Excellent. So I think that's very good. So so the next thing I come to is this very important class. Yeah, please go ahead.
So that question in the previous slide was, so all retreating edges are back edges. So was that answer yes? Because when
all back edges are always retreating edges, but all retreating edges may not be back edges, right? It's a no, right? Because we saw that case, right? Because this is a retreating edge.
But there was no back edge here.
But there is no back edge, right? There is
there is no back edge. So okay. So I wanted to see a case where there is a retreating edge and it is not a back edge. So, but there is no retreating edge.
This is a retreating edge. This is a retreating edge.
Okay. But there is no back edge in this one.
But there is no back edge. Like if I take this DFS traversal.
Yeah.
So this is a retreating edge, but there is no back edge. This is surely not a back edge. Right? This is not a back edge because 4 does not dominate 3, right? So there is no relation between them.
Yeah.
Okay, good. So, okay, what now? So now we'll come to this very interesting category of graphs, what are called reducible graphs, reducible flow graphs. And I'll talk a little bit about why they're important. And many times in the next week, when you talk about a lot of analysis, you would see that these analyses actually are only designed, or at least are more efficient if it's a reducible graph. It is not a reducible graph, you will see that it can be much more inefficient, or an algorithm might not even work. Right? Some algorithms specially designed for this category of graphs. So what is a reducible graph? The way I will define it is by just listing out its properties. I will say that saying that something is a reducible graph is the same as saying that every retreating edge is a back edge. Remember that in a general graph, every retreating edge need not be a back edge. We just saw that example. But if it is a reducible graph, in that case, every retreating edge will become a back edge. If that is the case, it falls out that it will surely have a unique DFS tag, because my back edges are uniquely determined. And if my back edges are uniquely determined, then by this particular point, my retreating edges are uniquely determined. If my the retreating edges are uniquely determined, then I remove the same nodes when I create the DAG, and then my DAG will be the same. Right? That is also very clear. Right? So I'm giving you the very hand wavy proofs, but these are proofs to why this is right. And another very interesting property is that, by the way, before I move forward, are you clear with these three things? So, more importantly, why these two are equivalent? So these two are actually equivalent. So it's saying that, so I say something is reducible graph. So this is, you can say as a definition of it. That is one way to say it. So you can say, I'll say something is reducible if every retreating edge in that graph is a back edge. And if every retreating edge in the graph is a back edge, then it surely follows that it will surely have a unique DFS tag. That is very clear, right? Because now if we know that every back edge is a retreating edge. Now, if every retreating edge is also a back edge, in that case, I know that okay, so now every node is both a back edge and a retreating edge, or none of them. So now my back edges in the graph are uniquely determined. Remember, I mean, because they are defined by the dominance relation. So then I always remove the same nodes when I create the tag, because I remove the retreating nodes, the retreating edges. The retreating edges are the back edges. The back edges are uniquely determined. So we always end up removing the same node from the same edges from the graph to create the tag. And that is why the tag has to be unique. There is no other way. And there is this very interesting thing that you can do. There is something called these T1 and T2 transformations. I'm not sure if you have regional analysis in our syllabus, but so what they can do is that, so these transformations look like this. So if you have T1 and you have a self loop on itself, then you can apply the T1 transformation and you can simply remove the self loop. You can simply, I should not even say collapses, I should say remove. And the T2 transformation says that if you have a node which can have whatever, and it has a single successor, it can have multiple things, doesn't matter. But this particular thing is between A and B. B is the only successor of A. In that case, I can apply something called the T2 transformation, and I can collapse these two nodes. I can make one node which is both A and B, and all the predecessors of A become the predecessors of this node. All the successors of B become the successor of this. And I do not have to worry about, because, right, so I think that. Right, so so this is called the T2 transformation. Now, what this particular thing says is that if you keep on applying the T1 and T2 transformation again and again and again and again on a reducible flow graph, then you will end up with a single node eventually. It's a very interesting observation. Right? It's a very interesting observation. Right? Hats off to the person who came with this, but that's what it says. So if these things hold, in that case, if you keep on applying transformations like this, then you will always eventually come to a single node. And there are like this. So you can, for every T1 and T2, you can write transformations, and then you can say that, okay, I have no T1 something, I have a combination of nodes, and you can do an analysis like that. So anyway, I'll not get into it. Maybe somebody would cover it, I'm not sure. Now let us revisit the same fact for a reducible flow graph. So is the DFS-ST unique? It's still not unique, even for a reducible flow graph. That is very clear. right? And the example we saw in the last slide on the DFST not being unique was already a reducible graph. So yes, even for this case, it is not unique. Is the classification of graph into this unique? No, it does not, because it does depend on the DFST, and the DFST is not unique, it cannot be unique. Are the back edges uniquely determined? They are always uniquely determined. They were uniquely determined then, and they are uniquely determined now. Are all back edges also retreating edges? Yes. Now, if you have a reducible flow graph, in that case, your back edges are also retreating edges by definition. Are all retreating edges or back edges? Of course, all retreating edges were. Oh, sorry. So this was already holding. I missed it. Yeah, but in this case, what happens is that with this property, so that is what we defined for reducible flow graph, that retreating edges are also back edges. So for a normal flow graph, the answer is no. But for reducible flow graphs, the answer is yes. And similarly, is the DFS DAG unique? In an arbitrary graph, it is no. But for a reducible flow graph, it is yes. Right? So the answers to these questions change a bit depending on if it becomes a reducible flow graph. Now, why did I do all this drama? Because like I can do some interesting things with all this, and there is a nice connection between reducibility and DFM. And so what you can do is you can test reducibility by the theorems we had seen before, right? So if a graph is reducible if removing all the back edges reduces the graph to a tag, right? That is a test for checking reducibility. So if you are given a graph and you want to check if this graph is reducible, all you need to do is you need to go and find out all the back edges. What are back edges? If the dominance goes in the other direction, remove all the back edges. In case of if it is indeed a reducible graph, then when you remove all the back edges, you would have removed all the retreating edges also, because the retreating edges and the back edges are the same in a reducible graph. And then you would have already surely been left with a DAG. So if you remove all the back edges and you're left with a DAG, then the graph is surely reducible. That gives you an algorithm for testing reducibility. The other thing is that if you know that the graph is reducible, if somebody tells you that I know for sure that this graph is reducible, then you do not need to use dominance information to compute back edges, because you know that retreating edges are back edges. So then you simply find out the retreating edges, right? And then just say they are back edges. End of story. Why? Because we know that in a reducible flow graph, all the back edges and the retreating edges are all the same. So I do not have to compute this expensive dominance. Remember this dominance computation, I said it's hard because it's a fixed point equation. You have to solve it, compute this dominance. But if you know that you are given but the DFS traversal is very simple. DFS numbering is very simple because it's just one DFS pass over the graph. So it gives you an easy way of calculating the back edges, easy way of identifying the back edges. Okay, good. So now why worry about reducibility? Why did I make such a big mess about reducibility? So the reason is that, as I said, program analysis is often easier on control flow graphs which are reducible. And there are special analyses that you can apply only to reducible flow graphs. And let me end up with this thing, reducibility for dummies. So if you think that this last check was still much strong because you have to compute these back edges, which requires you to compute the dominance relation and all that, I'll give you a very simple way of identifying. So it is a one-sided check. It is not a both-sided check. But it says that if you use only structured control flow statements, like if you only have if statements, while statements, repeat until, continue break, if you only have these structured control flow statements, in that case, you can only get reducible graphs. There is no way your control flow graph can be reducible. So it does not mean, so like the big culprit, the statement I left out is goto. So if you do not use a goto statement, your graph is going to be reducible. I'm hoping that I'm not talking about more sophisticated control flow constructs. So I'm talking about simple procedural constructs. So among the simple procedural constructs, if you do not have a goto statement, in that case, your graph is surely going to be reducible. It does not mean that if you use a goto statement, it immediately becomes reducible. That is not true, right? But if you have not used gotos, then it is sure that you only have reducible. And there is some caution to be understood that when you apply optimizations and transformations, it can make a reducible flow graph into irreducible. So you have to be careful. So it does not mean that your code is irreducible. It means the flow graph that I might get from a machine code is reducible. That does not mean that. Right? So there can be things which can make a graph irreducible. But this is a very important point. As long as so most of the graphs, most of the programs that you write will only give you reducible flow graphs. And if it only gives you reducible flow graphs, all the nice properties and the theorems that we saw in the last slides, you can use.